Hi, this is Brad Strabig. In this episode, we're going to be talking about Box 3.3, in particular, the FAO plan to bring water consumption in Malta more in line with sustainable water use and resource management. We're going to take a critical look at this FAO plan and look at just how difficult it is to achieve sustainability sometimes. The FAO design guidance and recommendations for Malta fall into several different categories. One particular example for engineering analysis is to look at all new development shall be provided with a water cistern to store water runoff in built-up areas. The volume of the cistern in cubic meters shall be calculated by multiplying the total roof area square meters by 0.3 for dwellings, 0.45 for villas, 0.45 for industrial and community buildings, and 0.6 for hotels. Thus, the amount of consumption and storage is going to be proportional to the type of unit for which that building is designed. Also, paved and hard surfaces could also consider surface water runoff catchment. The idea is to catch more of the precipitation, decreasing the terms for runoff and infiltration, and increasing available rainwater for uses for agriculture and domestic supply. We've already looked at some of the history of Malta water use, starting prior to the 1980s where there were pretty low levels of agricultural use, moving from the 80s to the last 30 years where there was a significant agricultural boom in olive oil and vineyards that led to increasing use of groundwater supplies for agricultural productions, but also for domestic productions as population and economic development expanded. How do we move forward in a more sustainable process to achieve a greater balance between groundwater inflow and outflow? The United Nations came up with several different scenarios. There are two different water demand scenarios. The first water demand scenario is that municipal demand remains fairly constant at current values or increases by 1% or 2% per year, while agricultural demand increases reach a maximum to not exceed 21 million cubic meters. The FAO provides advantages and strategies and effects and implications of different types of strategies. There are three strategies investigated. The first is that agriculture is given priority over the use of groundwater. Consequently, urban supply would have to increasingly come from reverse osmosis desalination plants. The economic and social implications of this strategy are that the public water supply would have to source its water from these desalination plants. The price of this water will increase with the price of energy because energy is required for water desalination. The quality of the domestic water supply may increase, however the country will be dependent upon reverse osmosis desalination plants and importation of energy and intensive energy use for creating domestic water. This will leave the country vulnerable to fluctuations in industrial and tourism sectors would be expected to reduce their economic competitive rates because of the increased cost for water for laundry, bathing, water use for hoteliers, and just water consumption. A second strategy is that no action is taken and groundwater abstraction remains unregulated. This is likely to lead to over-abstraction or overuse of the groundwater. This will increase salinity in the groundwater tables and dry up parched aquifers or already depleted aquifers, reducing water quality and make it unsuitable for both domestic water use and agriculture use. This will incur all sectors a long-term cost as groundwater becomes progressively unusable and must be imported from other places for water quality issues. The third preferred strategy is a reduction in groundwater abstraction to achieve a sustainable abstraction or balance between groundwater withdrawals and groundwater infiltration rates. The available quota of groundwater would be allocated with 50% going to domestic use and 50% going to all other uses. This would include agriculture and industry. Options involving artificial recharge of groundwater from both captured rainfall as well as treated wastewater or treated water would also be investigated. More efficient agricultural techniques and more efficient irrigation techniques would be encouraged for reducing water use in farming. The implications of this strategy are that the public water supply will reduce the proportion of abstracted groundwater, while agricultural industry will have to increase the amount of recycled water use. This would be achieved in part through the dual fee tariffs for domestic and commercial sectors, and agricultural sectors would have to absorb a cost associated with increasing treatment for the sewage that could be used for groundwater for watering and irrigation of some potential crops, potentially tree crops such as olives and vineyards. In the long term, this may lead to better groundwater quality and will reduce the long-term cost of water for all sectors moving into the future. The second scenario is that municipal demand remains fairly constant at about 1 or 2% a year, while agricultural demand actually decreases, in part due to poor water quality. In this case, agriculture could be given priority of groundwater use, with the public supply remaining largely dependent on desalination. The implication of this is that we'd have increasing costs associated with reverse osmosis and potentially reduced agricultural production and increased food prices. The preferred goal for the FAO, as stated for long terms, is to balance the sustainable use of water with the sustainable resource rates of water. This was the United Nations and Maltese government proposed a timeline for enacting regulations such as the dual tariffs, completion of economic analysis for water use for crops and industrial processes, implementing an environmental monitoring program to monitor water salinity levels and groundwater storage options, publication plans for public consultation, and programs of measure for operation and maintenance of water treatment plants and reducing leaks associated with water use. Regular review of the characterizations and impact assessment from various districts and economic analysis of water management practices and policies. By 2015, they had hoped to establish a sustainable water use, but this has yet to be analyzed. For future water management plans will be published and disseminated to the public in the years 2021 and 2027, according to this plan. Finally, we'll look at tourism, which is one of the growing economic sectors, and how this may affect water use. We see total annual production for tourism actually going down, the per capita demand per day basically staying the same. Tourism being an economic driver, can tourism increase and demand for water decrease through more efficient processes? This is one of the things that's required of hotel and tourist facilities in Malta, that they have ultra-conservative approaches to water use, both in terms of water supply and reusing water on site, so that any new facility has to be nearly 100% reuse of water within the facility for things like washing, cleaning toilets, and grounds irrigation as well. So the FAO has attempted to project the million cubic meters per year under various scenarios, but most of these all exceed the available 55 million cubic meters per year. So we're still very close, under even the best case scenarios, to not being able to comply with sustainable use of water in Malta. These are significant and non-trivial problems to dealing with water issues in terms of sustainable supply and reasonable demand. So take a moment and tell me, how would you fix this problem? What tools can we talk about for sustainable development that we can put to use? What are the options? Think back to chapters 1 and 2 as you think about this process. What are some of the tools that we've developed as engineers and scientists to bring things into greater alignment with water availability and eventually sustainable long-term use for intergenerational equity? We'll talk about other problems and case studies in other chapters as well. Thanks for your time, and next we'll talk about another important sector of applying mass balances to help us determine water quality as we move downstream from one place to another.